It will be discussed in this course. Grinding process, supporting roller for rotary kilns. What are the phenomena to begin the grinding process? Why resurface? Let's start the course. Supporting roller grinding. Key benefits: resurfacing of rollers and tires. 1. Reduces energy consumption. 2. Lowers operating costs. 3. Requires no downtime. 4. Prolongs service life. 5. Eliminates vibration. 6. Roller skew neutralized and set properly. Why resurface? Rotary kilns, cooler and similar types of equipment, stay in continual operation most of the year, and as time goes by various types of wear problems occur. Tire and roller naturally form irregular surface profiles from roller skew, in addition to pitting, spalling, irregular markings and rolled over edges. Now let's ask a question. What are the conditions, on the basis of which we determine whether the tires and rollers are resurfacing or not? 3 conditions require tire and roller resurfacing. Firstly, when a tire or roller outer diameter is tapered, the plane of the tire is not perpendicular to the kiln axis. This condition complicates the motion between the tire inner diameter and the kiln. In addition to the circumferential rolling motion, there is an axial motion component that causes high pressure on the stop blocks and rapid wear of the support pads. High stop block loading requires frequent repairs, but the accompanying wear of the tire support pads has the more serious consequence of increasing the tire clearance. High tire clearance reduces the tire's capacity to maintain a circular shell cross-section, and the ovality increases. Secondly, some piers have very high tire stop block loads. Despite uniform tire and roller radii, the high loads are due to improper support roller slopes. Note: the desired roller slope is often different than the kiln overall slope. Changing roller slopes is a difficult and precise procedure, particularly if the bearings do not have self-aligning ball and socket liner supports. Without such support, one bearing on a roller cannot be shimmed relative to the other, because the bearing liners would not then lie in a straight line. Both bearings have to be tilted such that the bearing liner load distribution is uniform after the slope change is complete. If downtime for a slope change is not practical, the problem of stop blocks pressure and support pad wear can be addressed by grinding the tire and the rollers with a 0.4 mm taper. This will result in a significant change in the angle between the tire plane and the kiln axis. Thirdly, if a tire or roller has a convex or concave load carrying surface, the Hertz pressure in areas of high load contact may be unacceptable. Resurfacing is required, given such conditions. The setup of a grinding machine is a technically difficult procedure. All tires have an axial runout, so the line defined by the points of contact between the grinding stone and a tire does not stay parallel to the grinding machine. In other words, the surface being ground moves toward and away from the machine near the tire edges as the kiln rotates. The machine design must assure uniform stone pressure despite this difficulty. To further complicate the setup procedure, the grinding machine has to be set parallel to the kiln axis, without the benefit of simple reference points that define the position of the kiln axis. The shell axis has to be located via precision measurements between the tire and the grinding machine, taken near the tire edges 90 degrees from the maximum and minimum extremes of the tire axial runout. The machine adjustment calculations must compensate for differences in the tire diameter, where the measurements are taken. Unless this technically difficult procedure is successful, it is likely that the tire will be ground with a taper, or more than the minimum amount of steel will be removed to achieve a uniform radius. Resurfacing decreases the radius of tires and rollers by as much as 6 mm. A radius decrease changes the alignment of the kill axis, at times resulting in shell ovality changes. After a resurfacing procedure, the ovalities should be measured and appropriate adjustments should be made. The resurfacing of tires and rollers always changes the angle between the roller axis and the tire axis. This results in a change in the thrust load between the tire and its rollers. This may result in increased pressure on the tire stop blocks, increased bearing temperature, because the bearing thrust mechanism pressure increases, and increased thrust roller load. It is important to assess these changes and make appropriate bearing adjustments. In view of these difficulties, plants should insist on high-quality control standards over resurfacing operations. This is best accomplished by actual plant oversight of the final radius measurements and roller adjustments. The tire or roller radius should not vary by more than 0.25 mm. The direction of a taper, if any, should be dictated by stop block load considerations. Tires with a high axial runout should have up to a 0.5 mm crown, otherwise all components should be straight to within 0.25 mm. Summarize this topic in several key points. As wear progresses, these conditions can result in vibrations, inability to control axial thrust, increased power consumption, alignment problems, and reduced bearing life. Without regular preventative resurfacing, issues such as premature bearing failure and damage to tire retaining components, bases, and drive components can occur. Rolled over edges lead to edge cracks, which can propagate into the tire, causing edge spall damage or the entire face of the tire to crack. Resurfacing allows for proper adjustment of support rollers and reduces power consumption, improves mechanical stability, reduces energy consumption and lowers operating costs. We resurface the worn faces of support rollers and tires in situ, while the Kiln rotary equipment is in normal production. Note: see video. There is no costly downtime, and plant operation is uninterrupted. Resurfacing is a process that restores the rolling surfaces of tires and support rollers. There are different designs of grinding machines according to each company to accommodate different face widths of tires and rollers and special situations that might occur. This machine can be easily manufactured on site. Two machines are typically used simultaneously, one on the support rollers and one on the tires. Reconditioning removes work hardening, and by working simultaneously on both components, this minimizes damage of the fresh surfaces before they can work harden. Tire grinding. Watch this video to learn how to grind tires for rotary kilns. Tire grinding is done with supporting roller grinding. Measurable results. Resurfaced components improve the mechanical efficiency of your kiln. Energy required to turn the kiln rotary equipment is reduced. Case studies show that energy savings of up to 42% have been made on the running of Rotary Kilns rotary equipment. We accurately measure and report the diameters before and after the resurfacing process. This makes it possible to hold a machining tolerance of 0.4 mm on the radius. The diameter measuring device used in this process is Circumferential Measuring Device, CMD. We will review some types of wear problems. Types of wear problems. Problem number 1. Concave and convex wear. Description: this problem results from normal skewing of the roller shafts. Contact between tire and support rollers decreases. Consequences of this problem: inability to control individual roller skew, high axial loading of bearings and potential bearing failure. Difficulty controlling axial positioning of the kiln rotary equipment and increased power consumption. The problem number 2. Rolled over edges. Description: this problem, sometimes referred to as mushrooming, this problem may have a variety of causes, although badly skewed rollers are often to blame. Consequences of this problem: serious metal failure, or entire cracked tire faces. The problem number 3. Taper wear. Description: this problem, conical wear, or radial taper, occurs when the diameter of the tire and roller decreases faster on one side of the face. Consequences of this problem: increased drive component wear, and kiln drive amperage, leading to higher kiln operating costs. The problem number 4. Timing marks. Description: this problem, horizontal or diagonal washboard patterns are imprinted on the rolling surfaces over a period of time by a poorly aligned gear and pinion. Consequences of this problem: pounding action quickly leads to mechanical failure. The problem number 5. Spalling. Description: this problem occurs when the face contact between the rolling elements has reduced to a point where the Hertz pressures exceed the elastic limit of the metal. Consequences of this problem: material peels off, forming spalls, or the material work hardens, cracks, and falls out in chunks, rapidly reducing component service life. An illustration of problem 1. Concave and convex wear on rollers and tire. Effects of tapered tires on alignment. If tire or roller wear is uneven, a taper condition often develops. This causes the plane of a tire to tilt relative to the kiln axis, resulting in a horizontal motion component between the tire and the support pads. The improper resurfacing of tires and support rollers adversely affects the alignment of a kiln by 1. Changing the alignment of the kiln axis. 2. Increasing the support roller thrust loads. 3. Causing stop block and support pad wear. These changes can significantly increase maintenance costs and breakdown frequencies.